I'm here to talk to you about private information retrieval in blockchain. Um, yes, so let's get started since we started a little late. Okay, so the topics I'd like to cover today, I'd like to try to explain to everybody what is private information retrieval. I'd like to talk about how can this technology help the Ethereum project and its community. I'd like to talk about why should we care about this philosophically. I want to give an overview of known techniques. I want to give some examples of practical deployments. I want to sketch how this could be used for Ethereum. And I think we might cut the future directions because I don't know if we're going to have time, but we'll see. Okay, so private information retrieval, often written PIR. So in private information retrieval, the idea is that there's a client and there's a server that has a large data set. And the client would like to search that data set for a particular key, but they don't want the service operator to learn what key they're searching for because it might be very sensitive for some reason. And so PIR generally means trustless cryptographic protocols that accomplish this task. So to try to connect this to Ethereum folks, I want to try to talk about a controversy having to do with Metamask, which happened last year. So in November 22, the maker of Metamask informed users that when you use Infura, which is the default RPC provider in Metamask, it will collect your IP address and your Ethereum wallet address whenever you make a transaction. And some people were unhappy about this because they felt like this is not what should be happening in like a Web3 technology. And so the options that we have now are users can use alternative RPC providers, but nothing prevents those providers from collecting the same data. Some users may run an Ethereum full node themselves for privacy, but unfortunately that's not practical for like the vast majority of users. So in principle, private information retrieval is a way that users could have that privacy without running a full node. So that's what brings me here today to talk about this. And I want to sort of talk about sort of how this connects to Web3 philosophy, right? So Web3 means different things to different people, right? It's a social movement. Web2 has largely become associated with giants like Facebook and Google that own large parts of the internet and harvest all the data in a model that's now called surveillance capitalism. And so I've been coming to East Denver for many years. I live in this area, and when you ask people what Web3 means, you invariably get lots of different answers. But one of the common denominators that I often hear is that Web3 means you own your own data. Now, I believe that you cannot meaningfully own your own data if you do not have privacy around that data. And that is what I believe motivates a lot of privacy activists to contribute to blockchain projects. So I want to try to give an example of private information retrieval in practice, because if you're an engineer, you may never have heard of private information retrieval before. It's not commonly used in real web technologies because it's actually really hard. But there are a few examples that I want to talk about. So 10 years ago, Signal Messenger ran up against a very difficult private information retrieval problem. So the problem is that Signal users need to be able to discover if their contacts are using Signal and get their public keys in order to send them messages. However, Signal does not want to learn your contact list. They don't want to be able to see or infer what phone numbers you're querying. They don't want to learn everybody's contact list in the whole world. That feels like a bad thing that they don't want to have access to. And there are a lot of obvious approaches they thought about, like what if we just hash all the phone numbers? But it turns out that that doesn't actually do anything from a cryptographic perspective because phone numbers are actually pretty small. There's not a lot of data there, and you could probably brute force the hash. So they wrote a blog post in 2014 about this issue because they were still thinking about it and they weren't sure what to do. And then they researched it for about 3 years, which I think is pretty interesting. A lot of private information retrieval research, there's a lot of academic literature on this topic, and most academic papers on this topic fall into one of two buckets. It's either computational PIR or information theoretic PIR. This has to do with sort of the security model for the system. In computational PIR papers, generally to handle a query, the server has to load every data item into memory and then do public key cryptography with it, which is very expensive. And unfortunately, these approaches generally just don't scale to having a service that millions of people are using in a large data set. In information theoretic PIR, they sort of changed the model. So there's not one server anymore, but there's K servers. And when you, the user, want to make a private query, you're going to send a special message to K different servers. And then those servers are each going to think about it and give you back a response. And then you're going to like do something with all the responses together, and you're going to get your answer, but the servers aren't supposed to learn what happened. But the problem is that this model assumes that these servers are not communicating, and there's no way for you as a verifier, as a user to verify that the servers are not colluding. So like, sort of put this in context, like, in my experience, a lot of people in the Ethereum community are pretty good at game theory. So there are a lot of blockchain technologies where you assume that the majority of the validator nodes are honest. And then that makes the consensus service have liveness and have good properties going forward. And we know that in principle, all the validators could collude and get together and start rolling back blocks and rolling back time or tampering with the blockchain in bad ways. But we also know that if they did that, it would be immediately apparent to everybody who's syncing the chain. They would not be able to conceal the fact that this happened. So we can trust them, but we're also in a position to verify that they didn't do that. Whereas with this information theoretic PIR stuff, it's like if all the nodes decided to collude and start sharing messages to try to see what your query was, they know that you would have no way of ever finding out that they did that. So that makes the game theory around this very bad. So I don't expect K-server PIR to actually be used in practice. Signal sort of looked at all this stuff, and what they ultimately decided to do, they created the Signal Contact Discovery Service, and they decided the best approach was to create an Intel SGX enclave. And so that's somewhat surprising, right? It involves trusted hardware, so it's a complicated solution. But the shape of Signal Contact Discovery is roughly like this. The data set is stored in the enclave's encrypted memory, which the node operator is not able to access without penetrating SGX protections. And when users connect to this service, they create a secure connection to the enclave using remote attestation. Then the enclave scans across the entire data set, all the phone numbers and all the public keys in constant time in order to resolve queries. But many queries are actually batched together for many users to try to amortize the cost of this slow scan. And then several minutes later, all the encrypted responses are returned to all of the users. So that's a pretty remarkable thing. And to connect it back to Web3 philosophy, to my knowledge, this is the first private information retrieval service that was ever deployed to serve millions of users in real life, like not as an academic paper. And I think it's really cool that Signal was not content just to promise we won't log your data. They want to use cryptography to prove that they are technically incapable of harvesting your data and eliminate the need for blind trust. Now, I believe that that is a social norm worth building towards to counter surveillance capitalism generally. And I also think it's cool that, like in my view, this aligns with a lot of Web3 privacy projects, even though Signal's not a Web3 company, and they're like, in some ways, a lot older than Web3. So the next thing I want to talk about is Oblivious RAM, which is sort of another iteration of this. So Signal Contact Discovery was great, but the algorithm they used is pretty rudimentary. It still requires touching every data item in order to support a query. It's not really appropriate for a low latency service. A lot of blockchain stuff, a lot of payments applications, you need to be able to respond in seconds, not minutes. Signal was okay with having contact discovery be like, it takes 5 minutes to find your contacts because it was an adequate user experience for their needs. Most people don't immediately need to find their contacts. As long as they get them eventually in the background, then it's fine. But we were sort of interested in trying to figure out how we can make this better. And so we turned towards a technology called Oblivious RAM. So Oblivious RAM is a data structure with a cryptographic security property. It does not require touching all the data in order to serve a request. Instead, what happens is data is continuously shuffled over time in a way that provably obscures the flow of data across all queries. And together with the secure enclave approach, this can be used to build a low latency private information retrieval service. So I want to try to talk about the history of this idea because it's pretty cool. So Oblivious RAM was invented by Oded Goldrake in 1987. That's actually before I was born. It was significantly improved by Goldrake and his student, Ostrovsky, in 1996. PathORAM was a major breakthrough in 2013. That was due to Emil Stefanov, Elaine Shih, Christopher Fletcher, and like 4 others. This was one of the first Oblivious RAM data structures that had good theoretical worst-case performance. And then a few years later, Zero Trace was a landmark paper of Sajid Sasi, Christopher Fletcher, and Sergei Gorbanov, which first implemented PathORAM in an Intel SGX enclave. They had this idea that this might work, it might be good, the security model makes sense, and they decided to try it and do benchmarks. And they reported promising performance measurements on real hardware. So that was a really exciting paper. Of the 3 people pictured here, I would imagine that more people in the audience will recommend the third person, Sergei Gorbanov, because he went on to be a co-founder of Algorand and later Axelar. So I want to give a shout out to Sergey. So this is where MobileCoin enters the picture, where my story touches onto the thread. MobileCoin launched an Oblivious service called MobileCoin Fog in February 2021 to support mobile clients like Signal and Mobi in a privacy-preserving manner so that they can check their balances against the blockchain without revealing to us which transactions are theirs. we actually load the entire MobileCoin blockchain into Oblivious RAM. And we support all the mobile users' balance checks in real time. This is the first time that Oblivious RAM technology was shipped in production to millions of users. We built on the ideas of Zero Trace, and we implemented a number of performance optimizations to make it practical with only a few actual machines. All of our machines are serving about 100 requests a second against the whole blockchain loaded into these ORAMs. And so at this point, I want to give a shout out to all the engineers that I've worked with, because there's really have been a lot of people that have made this a possibility. So I designed and prototyped Fog. I implemented our ORAM in 2019. A large team of people has worked together over years to productionize and scale this into the future. So I want to give a specific shout out to my colleagues Eran Runstein, James Cape, Joe Kotke, Joey Yandel, Sarah Drakely Hall, Sam Deely, William Juan, Jason Greathouse, Andrew Riggle, and Emily Cutlip, as well as some other people not pictured here, including Nick Santana and Ramon Meches. So thank you all of you. I'm extremely proud of what we've built. So now I want to talk about how Oblivious RAM could help Ethereum. So the Ethereum blockchain is quite large. However, I believe that it could be shared across a reasonable number of Oblivious RAM machines. I believe that we could load significant chunks, if not all, of the Ethereum blockchain into Oblivious RAM. The goal of this project would be to create a new ETH RPC endpoint that you could use in Metamask. And the idea would be that it would use ORAM to serve the types of requests made by Metamask while preserving the privacy of the users. The idea would be that this would be like a public good that helps users of Metamask to protect their privacy without having to do really complicated things like run a full node. Now, in order for this to work, we would have to modify the RPC protocol a little bit. We would have to allow for remote attestation to take place before the client sends an encrypted request to the enclave. This is not just like a drop-in change, but I think it shouldn't be too difficult to do that modification. Much of the infrastructure that we use for MobileCoin Fog could be reused for this purpose. It's mostly agnostic as to your structure of your blockchain, and all this stuff is open source. You can look at the MobileCoin Foundation GitHub. We have the MobileCoin repo and the MC Oblivious repo. In the longer term, I think it's possible to support the more complicated RPC requests, like ETH call, but there might be a path to do that. We'd have to talk about it. If you are interested in contributing to such a project or supporting such a project, please reach out to us. We'd be super stoked about trying to support the Ethereum community. The last thing I want to say is that I want to make a final note so to help people keep all these technologies straight. Oblivious RAM is not the same as zero-knowledge proofs. It's not directly related at all, actually. There is enormous interest and research effort towards using zero-knowledge proofs in Ethereum and Layer 2s. However, zero-knowledge proofs actually do nothing to solve private information retrieval problems. It's completely orthogonal. Yet, zero-knowledge proving attracts most of the attention. So in the long term, I want to sort of encourage us all to think holistically about privacy. How am I doing on time? I guess I have a few minutes. So I'm actually going to talk about future direction. So the last thing I wanted to talk about, which is kind of cool. So in a recent blog post, Vitalik Buterin on the Ethereum research blog talked about stealth addresses, what they are, what they mean, try to introduce the concept, and he even proposed that they could be added to Ethereum in the future, which is really cool. So stealth addresses are the idea that when you receive a payment, this is sort of a high-level explanation, your address is going to be perturbed randomly by the sender in sort of a special way, and this random address is what appears on chain to any onlookers. The idea is to establish unlinkability between your payments, so that instead of having your address on every single payment, you have these different stealth addresses on all of your payments. And then it may seem bad that your address is different, but it turns out that if you do the math correctly, later you can use your private keys to account for the perturbation, and you can still produce a correct signature to spend the stealth address funds. So that's a really cool idea. I believe this idea originated in Monero Research Labs. MobileCoin uses it. Zcash has sort of an equivalent idea. They don't exactly call it stealth addresses, but it's similar. One of the main issues about stealth addresses in my mind is that stealth addresses create scalability problems. So the reason they do is that the randomness for your stealth address is being chosen by the sender, and it's not known to the recipient in advance. So what it sort of means is that the users are forced to do trial decryption in order to identify their transactions. Like, if you send me a payment, I have no idea what the stealth address will be that it's coming on, so I have to look at all the payments and try to match my private keys against them. And this is a really bad thing for small clients like Metamask or mobile phones. That's why we were really focused on it at MobileCoin. So I invented a concept that I call sequential stealth addresses, which are a really key part of MobileCoin Fog. And in this variation of the idea, it's like your payments come along a sequence of pseudo-random addresses that are predictable by you, but nobody else. And so then you can search for your next payment using a PIR query, and you don't have to do trial decryption. So that is sort of what makes Fog able to do things in real time for people. We don't stream the entire blockchain to the phones because that wouldn't work. We use the sequential stealth addresses and PIR together to have privacy and scalability at the same time. So I don't have time to fully properly explain that, but if you are interested, please come up and talk to me after, or somebody else at MobileCoin, or you can look at the Fog white paper, which also explains all these ideas in great detail. So that's all I plan to talk about. I think we might have a minute or two for questions. Thank you all for listening to my talk.
You mentioned there were two approaches to PIR, one of which involves putting everything into RAM, basically, and that doesn't scale. But it sounds like the approaches you've used here also involve that for the whole blockchain. Like, is the idea then to scale that across machines and use the RAMs of multiple machines? And if so, can you then not correlate, like, which machine are you querying to find out what part of this data you're querying?
That's a great question. So the way the system is designed, actually, is that as you scale up to the highest degree, what I think we're supposed to do in the end is you store the ORAM pages, you actually move them out of the enclave, encrypt it again, and you store them on an SSD. And if you have a performant SSD, then that's actually not the bottleneck. So usually you're going to be having like, terabyte of data on each machine that's doing this, I think is like where the scaling rate works out to. And then when you're serving requests on the blockchain across several machines, what you actually do is you have like a router that handles the incoming request, and it dispatches to any possibly relevant enclave. So all the machines may potentially do work for your query, but usually when somebody's like checking their balance, again, having checked it like yesterday, they don't have to scan all previous blocks for their most recent payment. Instead, they just search the most recent blocks for their most recent payment. And that improves the scalability of the system a lot. But yeah, thanks for that question. It's a great question. Are there any other questions that I can, or do you have any further questions? Okay, thanks. All right, I think that's a wrap. Oh, you have a question?
Are you familiar with NIM? A gentleman yesterday gave a presentation on a library to kind of like, oh, sorry. Are you familiar with NIM? Okay, yeah, so can you use the two together? So like NIM kind of like uses Tor routing to like obscure your Metamask transactions, like who like sent them and how it's received. Could you use that together with?
Yeah, so the question is basically like, can you use mixnets, Tor type routing, or what NIM does to try to improve your privacy as well and try to avoid linking your IP to the queries that you're making? And the answer is yes, you can stack all these technologies together with increasing benefits. But yeah, it's like if you're using mixnets, what you're trying to do is you're revealing to the server which transaction you're querying, but you're trying to dissociate your IP from that. Whereas with our thing, we're trying to make it so the server learns nothing, but they might learn your IP. So yeah, so if you use both together, the server should really have no idea what's going on. Cool, I think we are out of time, but thanks everybody. Yeah, and thanks East Denver.